Hey there, you're watching the Aussie BIM Guru, and today I'm covering how to do looping or recursion using the Anemone package in Grasshopper for Rhinoceros. So I'll be covering in this video just the fundamentals of what looping actually is from a computational perspective, and some examples of recursion as it occurs around us, and also just showing you how to loop using Anemone itself with a demonstration, and then I'll set up a basic loop in this, and I'll sort of add a few techniques along the way that you'll find helpful, and then I'll just show you some advanced examples that I've already set up as well. So computational logic inherently goes from left to right or input to output. So it's typically one directional, but Anemone gives us the ability, or Anemone, I keep saying it wrong, to actually go back and send data back to our input and essentially create a cycle of data. So this is sort of like creating a wait loop or something like that, where you send something back over and over again and keep using that new data to inform the function that goes to the data at the end. So essentially we do it again. So it's quite powerful. It gives a lot of abilities to undertake evolutionary tasks that can basically use data from a previous iteration to inform the next one. So essentially creating a loop. Recursion occurs in nature a lot, so we'll see it on a lot of plants and shells, for example, where we can see sequences or iterative approaches to form generation. So we can replicate that actually using Anemone if we code it properly. There's also examples of recursion in infinite natures in mathematics. For example, a Mandelbrot set, because a loop doesn't necessarily have to end. Highly recommend you look into this if you're interested in it. It's quite an interesting topic, essentially the mathematics of chaos or complex numbers. So very interesting. And also an example of basic recursion that we could use Anemone to solve is, imagine if you threw a football and you wanted to find out how long it took to hit the ground. So you could apply some basic factors such as gravity that reduces the lift of the ball, or you could add wind resistance and find out the landing point of the ball. Obviously you could use formulas to determine this, but it's much easier to use something like Anemone in order to figure out where it's going to land by actually simulating the forces applied to that object over time. There's more advanced versions of recursion that we can't typically use formulas to derive. These are things that are typically pseudo-random, for example flocking mechanisms of birds or insects, which we can actually replicate using Anemone and very complicated algorithms. There's some good topics and videos out there on YouTube already about how you might be able to set this up, but it's quite complex, so I highly recommend you don't begin here. Maybe this is a destination if you're interested. But also a really common example of a looping mechanism is what's called Lloyd's algorithm. So if anyone's interested in computational design, you might have heard of centroidal Voronoi optimization, which is essentially the principle that if you keep deriving the centroid of a Voronoi and reuse it for a generation of a Voronoi, eventually you'll reach almost a stable state where the Voronoi settles into a pattern that is almost equally spaced at its centroids. Or the centroids and the generation points are almost coincident. A good example of this is actually at this link on this website. So I might actually just quickly open this up just to show you sort of what it looks like when a looping mechanism is run over this. Someone's actually embedded this in their website, which is pretty cool. So it should hopefully load. Here we go. So you can essentially see it at play there. So it's basically generating new Voronoi from the centroids of all the Voronois, and eventually he stops introducing new Voronoi cells to the algorithm, and eventually it settles into a fairly stable state. So this can actually be achieved using Anemone as well. We're going to use a very basic example today, just so I can teach you the fundamentals of how to use Anemone for looping. And Lloyd's algorithm, whilst it seems abstract, is actually used quite a lot in remeshing algorithms, so simplifying the number of triangles in a surface or the spacing of triangles in a complex surface, where maybe originally the mesh doesn't have very equally spaced triangles, which we know can be quite challenging when you're sampling a surface or trying to reduce the number of polys, but optimizing the quality of the mesh that is returned. So Anemone can be downloaded at Food for Rhino, and essentially it gives you just a very small toolbar in Grasshopper itself, and we're going to be focusing on these two buttons today, basically a start and an end of a loop. I highly recommend you have a look at the other tools in here. Essentially they add controls like adding delays to your loops and some other interesting smaller mechanisms as well. So this is sort of what an Anemone loop looks like. So essentially we feed in initial data, we tell the loop how long we want it to go for, we send the data through and we send it back, and essentially it keeps iterating in this pattern. And in this portion of the script here, we can manipulate the data in order to send back a different set of data, and essentially that's what can allow an evolutionary process to occur, or a semi-generative process, you might say. So today I'm going to be using Rhino 6 in order to demonstrate Anemone in action. I'm actually going to be talking to a video because I can't operate Anemone on a remote desktop session because the iteration won't be captured well enough while it loops. So I'll be talking to a video today in a few parts. So part one is just going to deal with looping. So this is how you can set up a basic loop. So what I'm doing here is just drawing a polycurve, and essentially I'm going to create a point that's going to sort of travel along the polycurve in a loop along a different parameter. So I'm just going to set a curve to this, and then from here I'll set up a fundamental loop as well. So I think I'm just going to chuck down bifocals just so you can see what all the components are called. And I think from here I'm going to get an evaluate curve node. So this is going to let me essentially place a point at a certain distance along the curve. So I'm just going to feed in the curve here, and then I'm just for now going to set up a slider just to show you what I'm trying to do. So I'm going to make it a slider between 0 and 1. Currently it doesn't work the way I want it to, so what I need to do is right click on the curve and reparameterize so that I work between a domain of 0 and 1, and essentially that is the point that we want to animate along the curve. So our input data that we're going to be feeding through from Anemone is going to be the number of the parameter along that curve. And we're going to keep manipulating that number in order to animate it along the curve. So we're going to get a start loop and an end loop from Anemone. And you'll get warnings immediately when you place them down, because currently they're not set up in a loop. So we'll need to build that loop. So we're going to just connect our two streams at this point, and then we'll build an intervention in the data stream. But once you connect those two together and you add your initial data, your loop is technically satisfied, but it's not looping at all. So it hasn't got any number of iterations to go through, and that's all driven by the repeat node in the loop start. So I'm just going to create a little panel so you can watch the loop iteration count. That'll tell us what iteration of the loop sequence we've reached. So what I'll do is just set up a trigger with a button in order to be able to reset my loop. At the moment we have 0 repeats, so if we tell it to go through a certain number of iterations, let's say 100, you can see now our loop starts going. So you can see it's very quick. It's basically operating at 1 millisecond, I believe, as its iteration cycle. And you can see that the loop will continue until it reaches the maximum number of repeats. So what we can do now is actually process data throughout each point of that iteration. So I'm just going to create an addition node here. And I'm going to take my data each time, and I'm going to add a small number to it. So I'm going to add I think I'm going to add an increment of 0.01 to our parameter along that curve. So each time our parameter is going to move slightly further along the curve. And you'll be able to watch this number cycle through the loop, and also the data that comes out of the loop as well. And you'll see that they'll be coincident as the script runs. So notice that they move at the same time now, because essentially that is the data we're looping. So everywhere you see the word data, that's essentially referring to the same thing on the back end and the front end of the loop. So what we'll do now is actually feed this value into our curve evaluation. So we no longer need this slider. And essentially we're using this value to drive our point. And now you can see that Anemone is actually animating this point along the curve. So we'll just set our increment to 0.01. And there you go. You'll see that we have 100 iterations at the moment. Once it reaches past 100, obviously you're going outside the curve's domain. So at that point, it starts estimating where the curve would go if it kept moving at a tangent. So obviously, if you go way beyond the end of your curve, it will keep just moving out at a tangent to where it left, or an arc tangent. So you can see that you have to be careful when you're working with domains with an Anemone, because sometimes it doesn't work just by sending the loop off into infinity. If you're going around a circle, for example, it might be okay. So what I'm going to do now is set what's called a terminating or an ending condition. So I want the loop to know that at a certain point I want it to stop, not only based on a repeat condition, but on a geometric condition. So I'm just checking here, when my domain gets equal or greater to 1, I want my loop to stop. So you can see that because I've fed that in as my ending condition or my exit condition, it won't go past this point, even if my iteration count is higher. So that's pretty much the fundamentals of a basic loop. So what we can do now is actually add more variables to our loop. So if you zoom in on the start or the end loop, you'll get a zoomable user interface. So what you can do now is actually add additional variables to your looping cycle. So what I'm going to do here is actually start setting up a radius field, because what I'm going to do is place a circle along that point as it moves, and as the point moves along, I want the radius to change in size as well. And I'm going to drive this through a different formula. So you can see I'm just renaming that parameter everywhere that it occurs within the loop. So what I'm going to do is just give it another starting value of 10, and this will be the radius of the circle when my loop begins. So I need to create a circle by normal radius, or CNR, and I'll just connect that up to the point that I'm evaluating at. And the radius, I'll connect up to the radius field. And I think at that point, you can't really see the curve. There you go, now you can see it. You can see that curve is following the point as well as it moves along. But let's say we want to manipulate our curve now as it moves along, and we want it to get bigger. So we need to set up another looping condition. So we're going to set up another addition, and we're going to take our radius, and every iteration, we're going to grow this in size as well. So we're going to grow this by a factor of +2. So we'll feed this in as our result. And now as our point moves along the curve, our circle will also grow in radius because that number is being changed by the same loop. So you can actually loop a lot of data together at the same time, so quite powerful. And I can just turn off the preview for the point and now just see my circle instead. But in the background behind the scenes, that point's obviously still there. So what you can do now is use a function called recording. So you notice at the moment, I'm only seeing the current iteration of the loop. If you right click on the node and go record data, you'll actually see every single iteration that has occurred during the loop. You've got to be careful with this because it generates a lot of geometry. So if you're doing anything with like 3D objects or patches, you have to be really careful. So at the moment, I'm just seeing that reset there. And the reason why I can't see any circles coming through is because the circle doesn't belong to the loop. But you'll see here that that data for the evaluated curve point is stacking. So that's what I want to do with my circle. So what you actually need to do is add the circle as a static variable to your loop cycle. So every loop iteration, I want to store the circle at that point. And you'll also need to add it to the front of your loop so that you can keep sending that circle through the loop as data. But essentially you don't really need to do anything to the circle itself because all we're doing is storing it. Sorry, I just did a graft there by accident, ignore that. So we'll send the circle across, and actually no, we won't even send it across there. I think we'll just connect it up to the end so we can store it on the record. And now, because we're recording our loop, we should see every circle at each stage of that loop process. So if I reset my loop, there you go. Now you can see the record process is tracking my loop, and all those elements are available whilst that loop is maintained. So you can see that there's a lot of potential for storing paths and elements, and obviously you can take these elements after and bake them or use them as the output to something else. So there's a lot of power to this aspect of the program, because you can see we've actually stored all those circles as a list. So you can do a lot with those, obviously, and this could be points along paths or polycurves generated through points. There's a lot of options. So I could turn this into a patch, for example, whilst I'm still holding the loop. But you need to be really careful that you don't necessarily do this whilst the loop is active, because it can be quite slow. But there you go. You can see we've taken those points and done something with them, all those circles. So yeah, pretty cool. But I think we'll jump on to the next part now, which is a loop that goes to infinity. Because at the moment we've set a terminating condition. Let's say we just want to keep looping until the user wants to stop. So this is typically more for things like relaxation-based processes, where the user needs to visually look at what's happening and determine when the loop should finish, rather than a geometric condition that can tell it to finish. So we're going to set up a stream filter. And what I want to do is, instead of saying that I terminate my loop when we get to 1, instead I'm going to say when we get to 1, go back to 0, and keep looping through that to go back to the start of the curve. So essentially our point's just going to keep going start to finish, start to finish, start to finish, until we run out of repeats. or I say stop. So I'm just going to say that when it is not true, keep sending through that number. When it's false, when it's not larger. When it is larger, send it back to 0 and then send that data back through. So I'll do that, and I also need to disconnect my exit condition as well. So now my loop has no exiting condition. And once I reset my loop, we should see that occur. So now you can see it's going to go from the start to the end, but then it's going to keep going. And note that when it goes back to the start of the loop, the radius value is still getting bigger. So it's not resetting all the data, it's only resetting that parameter point that I've nominated. So you can see there's a lot of potential for pattern finding and geometric convergence with this method. So there's a lot of potential with this as well. You can see I'm almost creating like a spirograph function through this mechanism. You can see it's getting a little bit slower because obviously I'm putting in a lot of data at this point. You can change your repeat trigger at any time to a lower number to stop the loop, or you can also change it to keep the loop going to a certain point. I find these can be enough to control the loop sometimes. Depends on how fast your loop is operating. So that's pretty much how to run a loop to infinity. But in the next step, we'll be looking at how to pause our loop instead, and also how to interfere with the data as it loops. So you can see it's still looping here, so I'm just going to reset it just to make my circle a little bit smaller. So what I'm going to do here is set up what's a pause condition. So the loop cycle is dependent on 3 things. It's dependent on the pointer parameter, the radius, and the circle. So if any one of these 3 pieces of data doesn't make it to the end, the loop will pause until it gets that data again. It won't break, it'll just pause. So what I'm going to do is set up a stream filter with a false start toggle so that when the user opens the script again, it will be false by default. But note, as soon as I make this true and I break the stream, all of these things fail to collect data and the loop will pause. So that's quite surprising. I sort of expected that it wouldn't pause when I first did this. I thought it would just break and say you must start the loop again. But the moment that I unpause or go back to false, check it out, it just resets the loop. So pretty cool. So that essentially can stop your loop at a certain point when you're saying, I want to stop right now. So pretty powerful. So what you can also do, which I'm going to do here, is you can set up data that can be changed during the progression of the loop. So at the moment, I've just been working with a fixed increment to change the radius of that circle by. Let's say I want to sometimes make it smaller, sometimes make it bigger as the loop progresses. So what I'm going to do is set up a value list. So I'm going to say that no change is 0, slow growth is 1, normal growth is 2, slow decay is -1, and I think fast decay is -2. So these are going to be the factors, or normal decay. These are going to be the factors by which my radius changes depending on which one I nominate. So when I'm on slow growth, I'll be on 1, for example. So what I can do with this is I can start looping. And as I loop, the user can just keep changing this. And note that it gets faster if I'm on normal growth, it does nothing on no change. And then it gets smaller again on slow decay, and normal decay, it gets smaller again. But look what happens if it goes below 0, the radius starts inverting itself and the circle gets bigger again. So I don't want this to happen. I actually want it to get back down to 0 and stop and wait for me to tell it to get bigger again. So I'm just going to set up an interfering condition just to override. So whenever this is going to be less than 0, instead I'm just going to call on the number 0 and make that the current growth change rate instead. Otherwise I will let the growth rate be the actual growth rate. So I'm just going to connect up a gate here, and I'm going to say when it's false, so when it isn't smaller, I'll just take the current modified value. Otherwise I'll take 0 as my value to change my radius by. So I'll keep my radius at 0 at minimum. And now if we reset our loop, and I'll just probably add a couple of panels here just to show what's happening to the values. But as you can expect, we're not going to be able to go below 0 now. You can see at the moment that -203 is being overridden to 0. But you can see even though I've reached -2, what's actually happening is my radius is being set to 0. And then as soon as it starts growing, they start growing together again, either way. So that's just sort of how you can connect up an interfering or a dynamic condition throughout the condition of your loop. So hopefully that sort of helps show you all the techniques that you can use, and then obviously I can start recording as well. So as these change, obviously I can start seeing different cycles and patterns emerging. So quite an abstract loop, obviously, but shows you the fundamentals, I think, of how you can manipulate these. And I'll show you some examples of things that I've set up myself and some examples that I've downloaded. But there we go. So that's my resultant form from looping. Pretty cool, right? And that was all just created in like maybe, I don't know, 15 minutes. So let's just look at Lloyd's algorithm in Anemone. So this is actually a sample from the package for Anemone. But essentially I'm just taking a Voronoi, taking the centroids, and using those again to generate a new Voronoi and feeding that back into my loop until I essentially reach a settled state that the user's happy with. So I'll just trigger the process, and you can see the settling process occurring there. So it gets closer and closer as it cycles through, and it's quite quick. I mean, that's generating a Voronoi once every millisecond, quite impressive. And I can obviously cycle the seed of randomization, and you can see just how quick it is to really pick up a new Voronoi pattern and settle it. So pretty cool. There we go. So that's one example of what you could do. I think I'll jump on another one soon. Yeah, so I think this one's just a little example I found that I thought was cool. Just a simple iteration to generate a snowflake form. So dividing up every single triangle into more triangles in order to generate different shapes. So obviously you can use this sometimes just to run through a fixed number of iterations. So in this case, we just say we only want to go down to the triangulation point of 5. This one's a tree branch, so again, a finite recursion here, but essentially someone just programmed a set of tree branches. This one again, I think, is in the Anemone samples. So that's quite cool. You can see you can change the number of branches, the angles, and also the count of iteration as well. So pretty cool. And there's probably potential there. So this is one that I set up based on a tutorial. This one's actually setting up some fields to move points around. And this could be used for something like pedestrian flow modeling based on points of attraction. But essentially it starts pulling the points and moving them. So you can almost see that I'm pretty much simulating like a gravitational orbit field at the moment on these points. So pretty trippy. And I've built it so I can add more spin forces just to make things even more complicated. So pretty neat. And I've built the script as well so that I can reset it and also change things like the strength of the spin, so I can obviously stop things moving whenever I want. And I can dynamically keep changing those forces as I go. And I can obviously reset this as well to sort of do like a more stable form. So what happens with these points eventually over time is they sort of find a stable state or a form that sort of satisfies their outlines. So it's pretty cool. There's a lot of potential with this workflow. I haven't fully figured out what I can do with it yet, but it looks very cool at least. This is another example I built. I call this one like a magnetic cube. So essentially, I'm getting a point to be generated anywhere in the cube to go to a random point on the outside of the cube, and it will just move towards that point until it gets there. And I've built it too so that I can change the seed of where the points are placed. So as I cycle the seed, the point will find new destinations to go to. And likewise, I've also added the option to add more points that get added to lists. And then I've made an algorithm that changes the color of the lines. The shorter the lines get, the more through the RGB spectrum they go. So pretty funky, and you can see that I can keep changing the seed whilst I'm iterating. So quite powerful. And I'll keep going through the loop even though I'm changing the direction all the points go, just based on a simple algorithm. So pretty funky. So that was a fun little example to set up. But the last one, I probably had a little bit too much fun with the last one actually. This one, if you're on my LinkedIn, you might have seen it. It's a little bit on the ridiculous side, but I think you'll enjoy it. This is just the RGB spectrum I set up. Cool. All right, the last example is actually a video game that I made using it. So essentially I just made one where you have to protect this circle in the middle from all the enemy circles that keep generating using the looping function, and they get pulled towards there at like random velocities. And as you contact this sphere with the smaller one, which you control with a multi-dimensional slider, you absorb the enemy spheres, generating more in the process. And every time a sphere gets to the middle, a looping counter adds a number to the middle. And you can see in the bottom left, that's the iteration counter's remaining cycles to go, so your timer, essentially. So this is sort of my way to test my looping skills at the end. Really fun challenge, and obviously it's a little game too, like it's pretty cool, interesting way to teach people. So that's pretty much the way you could use Anemone, but there's a lot of things you can do with it from a computational aspect as well. Yeah, so hopefully that sort of shows you an interesting package and really simplifies how to set up those loops. It took me a while to figure it out, but once I did, I found there was a lot of potential for what I could do with this package. So hopefully this helps you out. I make videos about 2 to 3 times a week, so if you're not already following and subscribing, feel free to do so. And if you have any topics or comments or requests down below, feel free to do so. And hopefully I'll see you in the next video. Thanks, take care.